Hello everyone, it's Mrs. Frickman. We started talking about complex numbers. And sometimes once we start getting to more abstract things in math, the question that always comes up, why are we learning this? What does this have to deal with everything that we're doing? I'm going to show you today some math that's going to be a little out of your comfort zone. But trust me, I want to show you the math behind what it is that you use on a regular basis with complex numbers. Here we go. So, like with all math, the question that always comes up is, when will we use this? Well, you might not use this right now, but if you are going to go on to different types of careers with upper level math, you may. But I want to show you, where does this come into your everyday life? First, just a little review. We know how to find the zeros here. Where it crosses the x-axis, we know that our zeros would be at positive -2, which is pretty easy to solve. Now, we talked a little bit about complex numbers and what happens when a graph is above the x-axis. Well, our zeros will become imaginary. Why? Because once we subtract over that 4 and take that square root, we have a negative. We're taking the square root of a negative. So here, our zeros would be at positive -2i because of this negative root. So again, to go over complex numbers, because we will need to remember this for what I'm going to be showing you. Square root of -1, that's where our I comes from. If we take I squared, that's taking square root -1 times square root -1, which is just a -1. Now it becomes a real number when we square it. If we take I cubed, that's I squared, which we know is -1 times I. So that's going to give me another imaginary number, but this time it's negative. If we have I to the 4th, it's I squared times I squared, which again becomes a real number. If we have I to the 5th, that's I to the 4th times I. So now this pattern goes over again. So whenever we have I, that's the square root of -1. I squared becomes a real number. I cubed becomes a negative imaginary number, and I to the 4th is another real number. This is important for what I'm going to be showing you. So we have this amazing formula, Euler's formula. So we have this imaginary number, because we have an I here, that is equal to a real number plus an imaginary number. Now I'm going to show you why this works. Now I need you to understand why this works before I can get into what is it that you're trying to show us, Ms. Frickman, with the real application of complex numbers. So we have something called the Maclaurin series. Now you're going to have to just trust me on some of this information I'm going to be giving you, because some of this information you will be learning once you take Calculus 2 in college, because I know you can get there. Now, what these series are saying is, if we wanted to have, so without going into too much detail, Maclaurin series is a power series that allows one to calculate an approximation of a function, input values close to 0. Now, this is kind of like the equation that I just showed you, except my E value has an I. So what if we take this same equation but put a IX right here? So every place that had an X now has an IX. Now if I look at this, this would be this whole quantity squared, this whole quantity raised to the third, and so on. So using the information I started with complex numbers, when an I was raised to an even power, it turned into a real number. So I could rewrite this like this. So just clumping together the terms that have real numbers and the terms with the i's, because whenever there was an odd exponent, then that left an I with that term. So this now looks like that same equation that I just showed you. So we can rewrite this now as e to the ix. This whole thing would be the cosine x, and this right here is my sine x. I'm going to deviate from what I'm actually going to show you something cool. Now I think it's cool because I like math, but using that same equation, if I put in pi for my x value, so wherever there was an x, if I put pi in, I can get e to the pi I would be equal to this e value is at -1, this e value is at 0. Again, you're just going to have to trust me. So essentially, e, which is going to be an irrational number that goes to forever, raised to a power of another irrational number that goes on forever times an imaginary number is equal to -1, which I think is pretty cool. But let's get back to business. I know what you're thinking. You're thinking, Ms. Frickman, thanks for all this, but really, why do we learn complex numbers? So I showed you something from Calculus 2. I'm going to show you something now that you're going to be working on in pre-calc. Now, one thing here, you can kind of see this is a dark blue. This is the graph of a cosine x right there. So that's what we would start off with. Now, this green and this purple graph that I graphed, now please be aware that this is just a sketch. But this will have a shift left or right. This one will have a shift left or right. Now, this is a continuous graph that keeps on going. Now, one thing that complex numbers can help with is knowing what the phase difference is. So if I have this cosine x plus 50, this green graph right here, it got shifted. So again, moving left and right. And I have this cosine plus 15 got shifted. I want to know the difference, the phase difference in between these two functions right here. So what if I have to try to figure out the phase difference? So what actually got shifted here? So what if I have to add two trig functions of different phases? So again, these have different phases. That means they did not overlap. That curve did not overlap one another. So what if I have to add these two together? This is where our complex numbers will start to come into play. So when I'm looking at this, I have a cosine, both of these. Now, if remember that equation that we had, I can use this equation, e raised to the ix. Now, our x value is going to be what this is right here. But if remember, that equation dealt with both my cosine and sine. This is imaginary, though. So we can deal with this value right here, but just focus on my real, because this is what I want to add. So I can replace my t plus 15 into my equation, and then I can also replace my t plus 50 into my equation. Again, when I'm looking at these two equations right here, I'm just going to be focusing on the real part because I want to add this to this. Now, taking those two equations, I raised to the t plus 15 and e raised to the it plus 50, now we can just use our property of exponents, which is going to be stuff that you learn starting in algebra. So I can do power, or I can multiply within both of these, and I could get this too. So my next property of exponents, if they're adding in my exponent, I can change that to multiplying with the same base. One thing I noticed when I'm multiplying with the same base, they both have the term EIT. So I can factor that out now. And now I have something right here, EIT, and then on the inside, E15I plus E50I. Now I can now use this same thing, going back to that Euler's formula that I showed you at the beginning of this video. Because now we have that same formula, EI to something can give me cosine of that something plus I sine of that something. Now I can figure this out just with my calculator. So I can plug this into my calculator and this into my calculator. I can just do the same thing with the EI to the 50. So it makes it a little bit easier once I simplify it down with no variables. Now I can add these two together. So adding these two together would give me this term. Now, just because I don't want to make this as long as possible, now we could rewrite this as this term right here. Now let's try to think back. Wait, what are we doing again? Why is this important? Ms. Frickman, answer that question. Let's get back into what were we actually doing. Well, we want to add two equations with different phases together. So then we could look at these two equations. That's what we said. We can look at the real part of these two equations, making it exponential. Then we were able to rewrite it. So just focusing on these two, e to the I-50 plus e to the I-15. Oops, I wrote that differently. That's okay though, because we're adding. So we found out that this whole thing is equal to this. So that's what we did so far. So now when we're looking at this, we can multiply this back in again. Again, this is just our algebra that we've learned before. So once we multiply in, this is what we have here. So when we added those two cosines together, we could simplify that equation like so. So now this is still, again, using that Euler's formula that I showed you of why does it work. Now if we plug this into my cosine and to my sine, we get this part right here. Remember, we wanted that real part. So we started with this, and we wanted that real part, and we got this. And oh my goodness, it's a happy dance. Well, Mrs. Frickman, that's great, but why? Why with the complex numbers? Why would we have to add two phases together? One example would be AC circuits. So let's say you have two voltages with different phases put into a circuit like so. I'm not good at drawing, so just to let you know. You need to first combine them into one before you can analyze it. So then you must change to the exponential form, which I just showed you, and you needed the complex numbers in order to do that. Now, I'm not going to lie. I'm a math teacher. I don't know a lot about AC circuits, but I do know that there are different things like capacitors or conductors that you need to use to shift voltage and current along it, because AC stands for alternating current. And there's a lot more to alternating current than what I know. But what's something that you use for AC circuits? Well, AC circuits are for high power and long distances. So a lot of times you use AC circuits in your house. So it's kind of like the power distribution that you might have in your home. So it's going to be things like refrigerators, dishwashers, other materials or other appliances that you have at home. Wait, Mrs. Frickman, are you saying that you need complex numbers to have electricity? No, I am not. All the electricity in the AC circuits are off of real numbers, but you do need complex numbers to make the math work. You cannot actually hold or measure an eye. It's not a physical platform. So, the next time you open your refrigerator door, you have an engineer somewhere out there that was able to use complex numbers in order to help them use AC circuits. And there's one out of many examples that you can have complex numbers.